Welcome to this lecture series in number theory. In this lecture, we will discuss three interesting puzzles and let us recall what we need. Essentially, all we need is just modular arithmetic, and that is essentially all that we have discussed so far. So, we just need to know these two facts about modular arithmetic, which I do not want to spend time recalling. Also, recall that previously we have proven these two special things. So suppose x and y are integers and 3 happens to divide the sum of squares of x and y, then 3 individually divides both of them, meaning 3 divides x and 3 divides y. We showed this, but if you do not recall, take this as an exercise. Similarly, we proved that if 3 divides the square of an integer, then 3 divides that integer. And later we will, not today, but later we will generalize this result to great heights. Okay. Some problems for practice. And now let us get started. So first puzzle. We are given an increasing sequence of natural numbers which are in an arithmetic progression. What does that mean? It just means that the successive differences are constant. That's all that means. Okay. What do we want to show? We want to show, or we are asked to prove that in this infinite arithmetic progression is hiding an infinite geometric progression. To be very, very formal and precise, what we are asked to show is the following. We are asked to show there exist natural numbers I1, I2, I3 and so on, such that AI1, AI2, AI3 and so on are in a geometric progression. I will explain what is a geometric progression, but let me first explain what the hell have I written. So we wanted to show that hiding in this infinite arithmetic progression is an infinite geometric progression, which means that one can find an increasing sequence of indices such that the numbers in this arithmetic progression corresponding to those indices are in a certain pattern called a geometric progression, which just translates to saying that the successive ratios are constant. So an arithmetic progression is a sequence of numbers where the successive differences are constant. And a geometric progression is a sequence of numbers where the successive ratios are constant. So I hope the problem is crystal clear. And it's a very interesting problem, right? In a sequence of numbers of one kind of pattern, there is a sequence of numbers of another kind of pattern. And whenever we are faced with a question like this, it is a good idea to experiment. What is the simplest example where you can test this proposition or this problem? You take the most easiest arithmetic progression. So you can take a1 equals to 1, a2 equals to 2 and 3 and so on. Basically the sequence of the natural numbers. That is clearly in an arithmetic progression. Does it contain an infinite geometric progression? Of course it does. Just take 2, 2 square, 2 cube. These are the numbers sitting in our original sequence and they are in a geometric progression where the successive ratio is 2. And you can play along more. Okay, and I encourage you to pause the video and try to solve the question before you look at what I'm going to discuss. Okay. So let's rephrase the problem a little bit. So rephrasing the problem, fix a positive integer d and a positive integer k. The problem is merely asking to show that, give me a moment, show that the set of those natural numbers which are congruent to k mod d contains an infinite geometric progression. So this pink statement is asking to show that there is a geometric progression infinite such that each of its members lie in this set. Now, why are these two problems equivalent? Well, just call this number k, so call the first number k and call the common successive differences as d. So all of these numbers are equal and call that number d. So then this is k plus d, then you have k plus 2d, k plus 3d, and so on, right? So this set is almost the same as that set. This sequence of numbers k plus d, k plus 2d, and so on, every number in this list is here, right? This list could be a little bigger than that. That's okay, because if k is a very big number and d is like a small number, then this set might be containing more things than the list k plus d, k plus 2d, and so on. However, if you can show that there is an infinite geometric progression sitting here, you can show that an infinite geometric progression sits in your original sequence. That is very easy to show, so I am not going to spend time on that. So let me just show this statement. Okay, and it's very simple. Again, I encourage you to pause the video if you didn't do it before. Pause the video and try to solve it yourself. It's very simple. We can just construct the infinite geometric progression immediately. So let r be greater than 1. Choose it so that r satisfies this congruence. In fact, of course, you can take, if you want to be more concrete, you can take r as d plus 1. But any r satisfying this congruence will work for us. So the punchline is the following. Then the progression k, kr, kr square, and so on, this is clearly an infinite geometric progression. This is an infinite sequence of natural numbers. It's not constant because r is greater than 1. This is a genuine infinite geometric progression, and each of its members is here, right? K is clearly congruent to k mod d. Kr is also congruent to k mod d because r is congruent to 1 mod d, right? So kr is also congruent to, what have I written? Kr is congruent to k mod d, kr squared is also congruent to k mod d, and everything is congruent to k mod d. So this is an infinite geometric progression sitting in the set, and that was the rephrasing of the original puzzle. So make sure that you understand this implication, why this statement implies the original statement. You should understand that. And also make sure that you understand this small piece of reasoning, that we can explicitly construct an infinite geometric progression sitting inside the given arithmetic progression. Any such r will do. Okay. Next puzzle. This is also pretty simple, but I want to illustrate a certain idea via this puzzle. So fix an odd integer, call it little a. We want to show that a raised to the power 2 to the power n is congruent to 1 modulo 2 to the power n, no matter what n you pick. So again, we should always test such small things to get a feel for these. So suppose we take the odd integer as 3. If a is equal to 3 and we pick n, say maybe 2. So the question says that 3 to the power 2 to the power 2 should be congruent to 1 mod 4, right? So n has been chosen to be 2 and a has been chosen to be 3. So we are just trying to verify that this is true. And of course, 3 to the power 4 is 81. 81 is congruent to 1 mod 4 because 80 is divisible by 4. So this is true, and similarly you can check for more values to be convinced. And I encourage you to pause the video and try to solve this for yourself. Alright, so let's look at a solution. And here this has nothing to do with modular arithmetic. I just want to illustrate the idea of mathematical induction. So the point is this. Suppose we have proven it for some n. Clearly this is true for n equals 1. So if n equals to 1, then clearly a is congruent to 1 mod 2. Since n is 1, 2 to the power n is just 2, so maybe I'll just write it as a 2. Clearly this is true. Why is this true? Because a is given to be odd. A is an odd integer is equivalent to saying this. So this is what we are given, and we can just raise both sides to the power 2 and still it would be true. Just basic modular arithmetic. Or more simply, if a is odd, then a square is odd. That's all that we are saying. And therefore, for n equals to 1, we have verified this statement. No matter what odd a you pick, this statement is definitely true when n is equal to 1. Trivial. Now suppose, and here is the idea of mathematical induction, suppose we have proven this. We have proven that this holds for some n. Somebody has given it for some n. Suppose somebody has proven it for some n. We will just upgrade it for a higher value of n, namely for n plus 1. So then we will show that this holds. And once we do this, we will be done. Why will we be done? This is basically what mathematical induction is. We have verified it for a certain value of n, namely for n equals 1. And once we make this implication that if we know it for a certain value of n, then we also know it to be true for just one bigger value of n. Once we make that deduction, then we already know it for n equals 1. This implication will prove it for n equals 2. Then we can again use it to prove it for yet higher value of n, namely 3, and so on and so on. So this is like a domino effect, and this is typically how mathematical induction is illustrated via a diagram. The first domino is easily tilted or whatever, easily given a nudge to, and that initiates a cascade of other dominoes. So I hope this reasoning is clear, that once you've proven this statement and this implication, that whenever the proposition is true for a certain n, it is also true for n plus 1. Just combining these two things proves it for every natural number n. Let that sink in if this is the first time you were looking at mathematical induction. If it is still unclear, I encourage you to do a quick Google and read from internet articles, or maybe look at my videos on mathematical induction in the playlist named Kickstart. I discuss it under the rubric of well-ordering principle. Okay, so how do we do this? Well, this has nothing to do with modular arithmetic. So since we are given that this is congruent to 1 mod 2 to the n, we have 2 to the n divides this difference by definition. Now, what do we really want to do? We want to show that this difference. You want to show that this difference is divisible by that number. That's what it means to write this congruence. So this number is what we will just factorize. This is nothing but a to the power 2 to the power n whole squared minus 1. Note that this is same as that. And now we can write it as the usual formula. So all we are using is the fact that x squared minus 1 is x minus 1 times x plus 1. That's all. So we have this. Now this is divisible by 2 to the power n, as written over here. Maybe I'll box it. So this shows that the first bracket is divisible by 2 to the power n. And this is divisible by 2. Why? Because the reason is, so this is divisible by 2 because, or maybe I'll write this symbol very nice, because a is congruent to 1 mod 2. So yeah, because a is odd, we know this. This implies a to the power 2 to the power n is congruent to 1 mod 2. But 1 is same as minus 1 mod 2. Right? Modulo 2, 1 is same as minus 1. Which implies 2 divides a to the power 2 to the power n plus 1. Or in other more commonsensical way, a is an odd number. So every power of a will also be an odd number. And if you add 1 to an odd number, it becomes an even number, which is to say that it is divisible by 2. So now this is divisible by 2 to the power n, that is divisible by 2. So the product will be divisible by the product of these two numbers, which is precisely 2 to the power n plus 1. And that's it. That proves this proposition. Very simple problem, but I wanted to spend time on it because I didn't want to go fast on this one. Mathematical induction is a very important problem-solving technique. Okay, the most interesting puzzle is for last. We want to show that this equation has no solution in natural numbers. What does that mean? It means that whenever you choose x, y, and z as natural numbers or you choose x, y, and z in the set of natural numbers or from the set of natural numbers, this will never hold. No matter what three natural numbers x, y, z you pick, there is no way this equation can be satisfied. Of course, this can be solved if you are allowed other numbers. I mean, if you are allowed irrational numbers, then you can, or real numbers, let me say, clearly you can solve this equation. The most trivialist solution is 0, 0, 0. Just substitute 0, 0, 0. That's a genuine solution to this equation. But 0 is not a natural number. So I hope the problem is clear. And again, I encourage you to pause the video and think about this. And I also want to mention that such questions are quite popular in many Olympiads. Okay, so we will learn a general principle by which one can approach such questions. I'm not trying to say that this general principle will always work. There are many tricks and tools that one can employ when faced with such questions, but this one is probably the most basic and most useful. So here is a solution. Note that we will proceed by contradiction. So suppose this equation, suppose x, y, z are natural numbers such that this does indeed hold. and we want to produce a contradiction, right? So then 3 divides the left hand side, or I will write it as this: x square plus 10y square is congruent to 0 mod 3. Let me write it that way. Why? Because 3 divides the right hand side, so it should also divide the left hand side, and that we have written in this congruence fashion. But this implies that x square plus y square is congruent to 0 mod 3. And the reason is just that 10 is congruent to 1 mod 3. Right? 10 is congruent to 1 mod 3, so we're just using modular arithmetic to just say that this, whatever this is congruent to this thing, mod 3. Anyway, I'm sure you follow. But now this means that 3 divides x and 3 divides y. This is what we recalled in the beginning, and and we had proven it in a previous lecture. Right? If 3 divides the sum of squares of 2 integers, then 3 divides the 2 integers individually. Wonderful. So now we can write, thus we can write little x as 3 times capital X and little y as 3 times capital Y. So yeah, I should also write that for some natural numbers x and y. Right? Since 3 divides x and x is a natural number, x divided by 3 is also a natural number, which we are calling capital X, and y divided by 3 is another natural number, which we are calling capital Y. Alright, so this equation, which we may refer to as star, so using this in star, that 3 times capital X whole square plus 10 times 3 times capital Y whole square is equal to 3 little z square, which implies, right? I've done nothing, just basic algebra. Now 9 divides the left hand side. 9 divides this and that. So 9 divides the left hand side, and therefore 9 divides the right hand side, which implies 3 divides z square. Right? If 9 divides 3 times z square, then 3 divides z square. Just convince yourself. But then this means that 3 divides z, as we recalled. Or you can prove it immediately if you like. So therefore, we can say that little z is 3 times capital Z for some natural number z. Alright? So from double star, using this in double star, we have, or maybe I'll call the lower one as double star, that's more convenient. So from double star, we have 9 capital X square plus 90 capital Y square is equal to 3 times 3z or 3 capital Z square, which is same as saying, and now I cancel out by 9 on both sides, so I get capital X square plus 10 capital Y square is equal to 3 capital Z square. And now notice something very strange has happened. We started with a solution to this equation, or basically we started with three natural numbers which satisfied this equation. And what have we got? We have got that we have the same equation We have the same equation, because what is capital X? Capital X is small x by 3. And similarly for capital Y and capital Z. So we have the same equation but with smaller participants. And again, let me remind you that these are also natural numbers. X by 3, Y by 3 and Z by 3 are natural numbers. So if we start with a solution to this equation, we can produce a strictly smaller solution in the sense that each member in this solution set is smaller than, or in this solution triple is smaller than the original triple. All we have done is just we are able to show that you can replace x with x by 3 and still retain an integer, y with y by 3 still get an integer, and z with z by 3 still get an integer, and these 3 new integers again satisfy the same equation. Right? And that should already ring alarm bells that you can just keep iterating this process. You can apply the same reasoning one more time to show that instead of x by 3, you can write x by 9 whole square plus 10 times y by 9 whole square plus, equal to 3 times z by 9 whole square. Just same reasoning applied one more time, with x replaced by x by 3, y replaced by y by 3, and z replaced by z by 3. And you can keep going and keep going. But since x is a natural number, you cannot possibly keep going. At some point, this will stop becoming a natural number. If you raise 3 to the sufficiently high power, x by 3 won't be a natural number. But this reasoning shows that x by 3 will be a natural number. So we have a contradiction. And you should be very clear about this. If it is unclear why are we achieving a contradiction, please stay on it. I think I've said it in the best possible way I can. So we have a contradiction, and therefore the assumption that you can find natural numbers satisfying star is false. This assumption is false. You can't. If you could find smaller and smaller and smaller solutions, but you can't find smaller and smaller and smaller solutions because in natural numbers you can't go arbitrarily small. Okay, so the general technique here is exploit divisibility. Try to show that you will arrive at a smaller solution, and show that kind of the same, show this recursive step that start with an equation, show that there is a smaller solution to the same equation, and you get a contradiction. This is called proof by infinite descent. This is just a cousin of induction. Infinite descent. This is just another way to say or use induction, or better yet, the well ordering principle, but perhaps it's more natural to call it infinite descent and think of it the way we have used it, rather than argue via mathematical induction as the statement stands. Anyway, so I hope this helped you with some understanding, and with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.